In the morning, we started with the proof of theorem, which we didn't complete. So let's finish this here. The theorem was this, that let T be a linear operator from V to W, some finite dimensional subspaces. A bit less talking, please. Thank you. And we said that for each such linear operator, there exists a basis. If you do not ask me to, if you do not want me to ask part of the proof, please stop talking. Okay. A basis, there is a basis B of V and Deepto, finish the proof. At least finish the statement. We wrote it in the morning, right? What is the theorem? There exists a basis B of V and there exists a basis D of W such that, very good, yes. So the matrix of the linear transformation T with respect to B and D is IR 0, 0, 0, where R is Oborto. What is R? Very good. Rank of the linear transformation T. Yeah. Rank of T. Okay. And then we also stated this theorem in the this was the version for linear transformations, and we also stated in the version of matrices, right? So this was the first version, and in the second version it was that. So let A be a matrix with m rows and n columns, then there exists matrix P in GLNF and Q in GLMF such that Q inverse AP is of this form IR 0, 0, 0. Okay. Do we really require this inverse here? This inverse, is it necessary? It may not be, because we are just talking about a matrix and the inverse of this, but note that Q is in GLMF, some invertible matrix, and we are just talking, multiplying with its inverse, but Q was an arbitrary matrix. So not arbitrary matrix, of course given A, Q is fixed, but we could have called Q inverse Q instead. So there exists some element of GLMF, because Q inverse is also an element in GLMF, some element in GLMF, some element in GLNF, such that the product of these three matrices is of this form. And so can one tell me why these two forms are, why, at least why this is implied by this, then we can come back. So, yeah. Right. Right. Yes. Yes. For change of basis, right? Yeah. Right. Yes. Right. for which the matrix of representation is this. And this is that. Very good. Thank you, Snami. So yeah, so that actually shows that these two are equivalent, because I mean you can also make the argument from here to there. Okay. Now this is, I mean this statement, what it says is, well, you recall we began the lecture with in the first class saying about row sorting and column sorting. So this situation is kind of similar to that. What it means by multiplying A with an invertible matrix from the left? Well, every invertible matrix is product of elementary matrices. That is, this is a set of row operations on A, and this is a set of column operations on A. So this theorem means nothing but, given a matrix A, you have a set of row operations. So at first you can reduce it in row echelon form, and then whatever you had. So if you have row echelon form, how it would look like: 1, some pivot, 0, 0, etc., and then another pivot, 0, 0, etc., okay, and so on. Okay. And at some point, maybe there are some non-zero entries here, right? So at first you reduce it to row echelon form, and then what you do, you make it column echelon. So you can swap columns, you can subtract, I mean multiples of this column, which have nothing else, suppose here, from this one. So now you can make the entry, this entries here. I am assuming the matrix form is this, but you, I mean this also. So if I'm working with a matrix like this, but since we are doing both row and column operations, this argument could be also used in a different way, I mean in the opposite way. So if in the row echelon form there are some columns where there are, I mean which are left untreated, you can now use column operations to make all of them 0. Okay. So you can club all the zeros here, like if you have pivots here at first, since you are allowing row operations, you can swap these things. Okay. So all the 0 columns you can put together, and then since you are allowing now a column echelon form, so you are subtracting the non-zero columns, or you are actually replacing the you are replacing the non-zero columns with some multiples of pivot plus these columns. So you could make this part 0, and of course you could make this part 0 by row echelon. How about this one? Is it always 0? Yeah. If it is not 0, where could what things could be there? Suppose it's a non-zero matrix. Okay. Then you do again row echelon form here. I mean row reduction here. Suppose you do row reduction. What do you get? Pivots, right? And we are saying that in the row echelon form, the only pivots are coming from here. But suppose you get some pivots, then you do row echelon again, and this goes into this part. Okay. So it's not exactly in the middle portion, but what I am saying is that this one could look like 1, 0, 0, 0. Everywhere else 0. Or it could be a nearly full matrix, that is all ones here, and the last row is just a set of zeros, and this one is a set of zeros. So we are allowing actually all these forms. Okay, that is some identity thing here, like even 1 cross 1 is fine, and then the rest of the things are full with zeros. Okay. Now, is this unique? What I mean is that suppose you have, you replace A with some other matrix. You multiply A with some Q dash from left and some P dash from right, and call this as, say, A hat. Okay. Q dash is some invertible matrix again of the right dimension. P dash is some invertible matrix again of the right dimension. Okay. And now the question is that whether this A hat will have the same rank as A. It will, right? Because you are multiplying with Q dash. So in this form, instead of taking Q, take the inverse of this, multiply with this one. So even you have A cap, you you will get a representation of A hat in the same form with the same R here. I mean, this won't change. This IR won't change as long as you are multiplying A with some invertible matrix from the left with some invertible matrix from the right. Okay? Because I mean, this from this you can make it right. Q inverse, Q dash inverse A. No, sorry, A hat. P dash inverse P. Okay, and that will be exactly. Sorry, P dash here. P dash inverse. Excuse me. And that will give you exactly Q inverse AP, which is of this form IR 0 0 0. So what I mean is that you cannot change the rank of a matrix by multiplying with invertible matrix or with an invertible matrix from the left and an invertible matrix from the right. Okay, it is I mean, since this one is still an element in GLMF and this one is still an element in GLNF. So you are, I mean, A hat is just replacing A with after multiplying two invertible matrix from left and right. That is, you are doing some row operations and some column operations on this, but that won't change this rank R. Okay, we are going to use this observation in a moment. Okay. And this should also be clear from the point of view of representation of a linear transformation, I mean matrix of a linear transformation with respect to some basis, because you see that this is again the representation of the same linear transformation T with respect to some other basis. Okay. So basically you are, I mean, if you run Q dash and P dash through GLMF and GLNF, you are getting all the matrices of representations, I mean all the matrices of the linear transformation with respect to different bases. Okay. All right. Now this is, I mean, since you can do row echelon first and column echelon later, and you are, I mean, intuitively you can always get some identity things here because you can club the pivots together and all the 0 columns together here after when you are doing the row echelon. It's kind of intuitive why we are getting this result. But now let's give a clean proof of this using the language that we have learned in the morning. Yeah, Monidip? Q dash a P dash. Well, I am just replacing A with such a thing, and I am saying that even if we are considering instead of A such a thing, it will have the same rank. Okay. I mean, it's not coming from anywhere. I'm just saying that this one is again representing this linear I mean, if A were a matrix of linear transformation of, I mean, if A was were a representation of T with respect to some basis B and D, then this one is also a representation of T with respect to some other basis. Why? Because if you go from B to B dash, which is equal to BP, and D to D dash, which is equal to DQ, then A goes to A dash, which is equal to Q inverse AP. We saw in the morning, right? So take this Q inverse now as your this Q dash. Take this P as this P dash. Okay. So that means there is some basis with respect to which the matrix of linear transformation of T, the matrix of the linear transformation T is A hat. Okay. I mean, I came to this because I wanted to say that in whatever basis you take, this form will not change. Okay. Okay. Now, as we promised, we are going to give a clean proof of this thing that this is indeed true by proving this directly via constructing a basis for which the matrix of the linear transformation will have this form. And the proof is, for the proof, we are going to use the trick that we have used also earlier while we prove while we have seen the proof of the rank 90 theorem. That is, we start with the basis of the kernel, we extend it, and then we see that the extended part is a basis of the image of T, okay? And we will use all of these things here. Okay. So let this be a basis of kernel T, okay? And you can extend it to a basis of B, right? B0, B1 as we did earlier. But we are not writing B0, B1, we would write B1 first now. We are just reordering, but that's also a basis, right? It's linearly independent and it still spans phi, right? So let B be equal to B1, B0, that is an extension from B0 to the entire space, be a basis of V. Okay. And we know that TB1 then is a basis of the image of T, right? We can extend this also, because image T, as we saw in the previous class, image T is a subspace of W. Okay, so you can extend this basis of image T to a full basis of W, right? Let D defined as TB1 D1 say be a basis of W. Okay. So now, what is the matrix of the linear transformation with respect to the basis that we have constructed? I think we can wipe this part out, because we saw that these two are equivalent and that this is kind of intuitive. Okay. But nevertheless, we are proving it now. Okay. So it just means that if you do the row echelon form, row operations first and the column operations next, your matrix is still row reduced. Okay. If you do the row sorting first and the column sorting later, your matrix is still row sorted. Kind of similar. The arguments for proving those are completely different. Okay. The first one was a combinatorial argument. That was the proof, the problem with which we were tasked in the first class, and this one is a simple linear algebraic technique. Okay. So we know that the matrix of the linear transformation is given by this A, right? Matrix of P with respect to B and D, right? Now consider this. T of B is T of B1, B0, and D is T of B1, D1, this times A, right? Now this one is T of B1. What is T of B0? It's 0, right? That means you have here T of B1, and this one is full 0, okay, which is giving you T of B1, D1. Before we write A here, note that it's a basis, right? TB1 was a basis of image T. Okay. So how do we express this in terms of TB1? Just the identity matrix. The columns would be just the columns of identity matrix. 1, 1, 1 at the particular point, as the coefficient of the particular vector there of the basis, and 0 everywhere else, right? Okay. And this is entirely 0. Okay. So also remember how many elements are in TB1? That is the rank of I mean, it is the dimension of image T, so the rank of T, right? So this is IR, okay, and yeah, that we know from the first one, and there is I mean, everywhere else there should be zeros, right? We don't require anything, any other. I mean, what I want to say is that just one at that particular position suffices, because you are having exactly the same element here and here. Okay. Now you are expressing this 0 as a linear combination of this and this. What is, I mean, what are the, I mean, this 0 is actually a set of 0 vectors. Okay. So, and remember, this is a basis. Okay. So the only linear relation among basis elements which gives you 0 is the trivial relation, right? So this is a full set of zeros. Okay. So we see that this basis, I mean, with respect to this basis, this is the matrix of the linear transformation. Well, now we see that this one is written in this manner and in this manner as well. So can we say that A and this are the same? Why? Yes, because it's a basis. So every linear combination of basis elements is, I mean, every vector has a unique expression as a linear combination of the basis elements, right? So from here we can immediately conclude that A is equal to this, since since D, which is T B1 D1, is a basis of W. Okay, A will be of this form. Okay, done. Now just one corollary, and what class do you have after this? Yeah? There are no classes? Very good. So your TAs will take maybe a little time to demonstrate a prove and have you seen a prove or disprove problem earlier in the previous course? You saw? Okay, great. So I was just wondering whether you know how to prove that. So either there is a proof or there is a counter example. Okay. So then you can just work with the example, I mean test problem. Okay, just 1 minute. I want to wipe this out and write down the corollary of this. The last corollary that we see before the midsem. Okay, so here's a corollary. Row rank of, okay, let A be in, I mean, M cross N matrix over a field F. Then row rank of A is equal to column rank of A. How do we prove this? The proof is just 2 lines when we use this one. Okay. So note that. Okay, we start with the column rank of A. Okay. And we know that there exists, so given A, there exists Q and P such that Q inverse AP is of that form IR 0 0 0. R is the column rank of A, right? We just saw this a while ago. I mean, there by rank we meant column rank, right? Now column rank of A, call this matrix Q inverse AP as A dash. Okay. Okay. So column rank of A, we know that this is equal to this R, which is also the column rank of A dash. Of A dash, right? Now note that that is equal to the column rank of A dash transpose, right? This is IR. So if you take the transpose, here you still get IR, right? So column rank of A dash is equal to column rank of this one transposed, okay? And that is equal to the column rank of A transpose. Why? This is also just one line. Maybe we write it here. A dash is equal to Q inverse AP, right? So A dash transpose is equal to Q inverse, P transpose A transpose Q inverse transpose. Okay. So you see A transpose, you are multiplying with this, some invertible matrix here, some other invertible matrix here, and you are getting this form, right? So this R we saw earlier, right? If we have a matrix, you multiply with two invertible matrix from both sides, its rank doesn't change, right? So that means this will also have the same rank as R, okay? And that's the proof. So Samarjit, you were here earlier, or you just came? You're here, so you went out for something? Okay. All right. So that's the final thing in our class. That is, in our class before the midsem, that is row rank of a matrix is equal to its column rank. Okay. Now I think it's time for Vishal and Snigdha to take over. All the best for the exam.